Hello, welcome in the 7th lecture of the course Convective Heat Transfer. In this lecture, we will be discussing about forced convection over a flat plate, but this time we will be considering uniform heat flux is applied at the plate. Okay. In the previous lectures, we have discussed the wall was at constant temperature. Here the wall will be supplying uniform heat flux. Okay. So let me show you what things we will be discussing over here. First, we will be studying the behavior of thermal boundary layer over a flat plate which supplies constant heat flux to the adjacent fluid. Then we will be discussing or we will be determining the parameters for non-dimensionalization of temperature, because in earlier case temperature was straight away, temperature non-dimensionalization came straight away because wall temperature was known, but in this case wall temperature is not known because we are supplying the constant heat flux. So what will be the parameter for non-dimensionalization, that we need to see over here. Okay. Then we will be deriving the non-dimensional energy equation along with the boundary conditions for uniform heat flux case. Okay. We will be showing both the limits, high and low Prandtl number in this case. Okay. And we will be mentioning the energy equation if we consider the viscous dissipation with constant heat flux. Now let me show you the situation what is happening over here. So this is the flat plate, let us say. Okay. Free stream velocity is u infinity over here, and the free stream temperature is T infinity, but in place of wall temperature Tw, now we are having the heat flux known, which is Qw, and it is constant in magnitude. Okay. So let us consider that we have to non-dimensionalize the temperature. So earlier we have done T minus T infinity by some temperature drop. Okay. So earlier it was Tw minus T infinity, but in the absence of Tw, my concern is what will be this delta Te. Okay. So let us try to find out that one. For that we will be starting from the boundary conditions, because now the boundary condition will be little bit varying. Earlier it was T at wall was Tw, now it will be minus K del T del Y at Y equals to 0, that means the wall, here Y is in this direction, cross stream direction. Minus K del T del Y is actually equals to a constant, we are taking that one as Qw. Okay. So this is the boundary condition at wall we are having, right. So if we do the scale analysis of this one, so for T we have seen it is of the order of delta Te, which is still unknown. So delta Te we have taken. For Y we have taken L. Okay. So delta Te by L is actually Qw. Okay. So this is the order of the equation. Okay. If we non-dimensionalize theta and Y in this fashion, so Y bar has actually replaced over here by Y, because Y is actually, we have considered Y bar L by L in the previous lecture. Okay. So from here you see this became very complicated boundary condition. We can reduce this boundary condition in a simplified form. Just if we can shed off this part and we can simply write down del theta by del Y is equals to some constant, that will be convenient for us. So we can choose this delta T in such a fashion that it captures all these other constants and make this boundary condition very simplified. So in order to do so, what we are writing, del theta by del Y at Y equals to 0 is equals to minus 1 we want, let us say. Okay. So we want to shed off all these coefficients. So in that case delta Te needs to become Qwl by K. Okay. So here we have got some idea of the temperature scaling, okay, in terms of the wall heat flux Qw. Okay. So this temperature non-dimensionalization scale we will be using for rest part of this lecture. Okay. So as I have showed, so theta will be T minus T infinity and delta Te we have replaced by Qwl by K over here. Okay. So let us try to see that how this is affecting the equations, energy equations. So we will be starting from the generalized equation. So this is the dimensional form of the equation, having conduction in the right hand side and convection in the left hand side. Remember here we have not considered the viscous dissipation part. Now if you try to do the non-dimensionalization, in that case it is becoming 1 by REPR. So what we have done essentially over here is that this x we have converted, x bar we have converted to x, y bar we have converted to y. As a result, this REPR came over here. Okay, so alpha is actually giving rise this Peclet number or REPR. Okay. Now let us try to go for the stretched variables. So y is becoming small y, and y is becoming small y into r e to the power half, and capital V is becoming small v into r e to the power half. Already we have seen in the previous lecture. So if we do so, then we can actually neglect the streamwise conduction term. Okay, so this 1 by REPR del square theta del x square can be cancelled, and finally this equation already we have shown in the previous lecture. Okay, where streamwise conduction has been neglected. Okay. Important thing will be boundary condition. Earlier we have seen that del theta by del small y was -1. Now as we have used capital Y and small y relationship like this, so here r e to the power half is coming in front of that. So r e to the power half del theta del y is equals to -1. This is capital Y, remember. Okay, and far away from the plate the condition will not be changing, so theta infinity is actually 0, tending towards 0. Now as we have done in the previous lecture also, that eta will be taking as capital Y by root over of 2x, similarity variable, and using this what we can do, we can write down u is equals to f dashed of eta, and v is actually 1 by root over of 2x f dashed eta minus f. Okay, so this we can take from your fluid mechanics knowledge. Okay. Then here let us define theta as a function of eta in this fashion. Theta is nothing but your temperature profile, non-dimensional temperature profile in x and capital Y coordinate, and that we are writing root over of 2x by root over of re into phi of eta. So here all these x and y is coming in eta. Okay, though root x is over here in this equation. Okay. Now if you try to do the differentiation of this one with respect to small x and small y, because those terms are there in your energy equation as we have shown in the previous slide. So here you see del theta by del y, first it becomes del theta by del eta into del eta by del capital Y, which is nothing but 1 by root over of 2x. Okay. So this del theta by del eta actually becomes root over of 2x by root over of re into phi dashed of eta, because these are not function of eta. Okay, so the only this is the function of eta, so this became phi dashed. Okay, and 1 by root over of 2x remains over here. Okay, so and these two terms can be cancelled from here in this equation. It simplifies to phi dashed by root over of re. Okay. So it can be written phi dashed is equals to re to the power half del theta by del y. Okay. So boundary condition, whatever we have showed in the last slide. So the boundary conditions, as we have seen here, it is del theta by del y at y equals to 0 is -1, and which we have shown over here after making small y to capital Y, re to the power half into del theta by del y is equals to -1. So that can be now converted to, theta can be converted to phi using this equation. So re to the power half del theta by del y is equals to phi dashed. So phi dashed will be now becoming -1. Okay, so phi dashed 0 is actually -1 is the boundary condition at the wall. Okay, and away from the wall remains same. So phi tends to 0 at whenever eta tends to infinity. Okay. Also we can go for the higher order derivatives of this term, which will be requiring for the energy equation. So del theta del y was here in this fashion. If we do the derivative once more with respect to capital Y, so this become 1 by root over of rex into phi double dashed. Okay. And if we go for the del theta by del x, this is also a term in the convection side of the energy equation. So this derivation gives you the final form of this fashion. So here you can find out the final form is coming as root over of 1 by 2 rex into phi minus eta phi dashed. Okay, so these are simple steps. You have to do the derivation of theta with respect to x. We are having two terms actually, root 2x and phi, both are function of x. So if you see over here, first we have kept phi, have done the differentiation with of root 2x, and here root 2x has been kept constant, and phi derivation we have done with respect to first eta and then eta's derivation with respect to x. Okay, and further simplification has given rise to this one. Okay, so all three terms we have found out: del theta del x, del theta del y capital Y, and del theta del square theta del capital Y square. So let us put in the equation. Okay, so energy equation which we have already shown. So first this is your u is nothing but f dashed. Okay, and this term is actually your del theta by del x. Okay, here I have derived, so del theta by del x is over here. Then plus v, so this is your v, okay, and then this is your del theta by del y, okay, phi dashed by root over of re, and in the right hand side, conduction side, 1 by pr, then we are having del square theta by del capital Y square. So this is the second derivative of the theta with respect to y. Okay, so this equation we can further simplify, and cancelling different terms will be giving us phi f dashed minus of f dashed eta f dashed eta phi dashed plus eta f dashed phi dashed minus f phi dashed is equals to 1 by pr phi double dashed. Okay, so if you just do the multiplication, all these terms will be coming. Okay, eta f dashed into phi dashed and f phi dashed. Okay, so these two terms can be cancelled. So finally the equation will be coming as phi dashed plus pr. So pr can be taken multiplication in this side. So pr into f phi dashed minus phi f dashed is equals to 0. Okay, and boundary conditions, as we have already derived, that phi dashed 0 will be equals to -1 and phi of infinity will be equals to 0. Okay, so this is the equation, and these two are the boundary conditions we have obtained. Okay, for constant heat flux cases. As we have taken this equation, theta to phi relationship we have taken in this fashion. So here let us try to see that how heat flux can be actually linked up with phi. Okay, so we know that theta already we have seen is nothing but T minus T infinity by QW L by K. So this was actually delta TE, our non-dimensional term, our dimensional term for the scaling of the temperature. Okay, and in the right hand side we are having the function of the phi, as we have considered theta and phi equation like this. Okay, so if you proceed further, then phi can be written in terms of T minus T infinity by QW by K root over of 2 nu x bar by U infinity. Okay, so phi we have written in terms of temperature. Okay, so if you try to find out phi 0, okay, so what happens at phi 0? So phi 0 means at wall, what is the profile of the phi? Okay, what is the value of the phi? So you can find out. So this will become actually TW, because T at wall is TW. So TW minus T infinity by QW by K root over of 2 nu x bar by U infinity. Here why we are doing this? Because we want to find out actually what is the value of TW, because in this case wherever we are having constant heat flux, in this case the wall temperature is unknown. Okay, so from here we will be trying to get what is the value of this wall temperature, right? So wall temperature, if you do the side changing and little bit of simplification of the previous equation, so wall temperature can be written in terms of T infinity plus QW by K root over of 2 nu x bar by U infinity into phi 0. Okay, so main task here, as QW is constant, we have to find out what is the value of phi, okay, at the wall. Once we can find out phi, we can get the value of the wall temperature. Okay, Let us also see what is the heat transfer coefficient Hx. So Hx is nothing but we know from adjacent layer which will be actually taking the heat via convection. So Qw is the wall heat flux which is constant divided by Tw minus T infinity. Okay. So Tw we have already defined over here. So Tw can be found out in this fashion. So this is K by root over of 2 nu x bar by u infinity into phi 0. Okay. So Tw minus T infinity can be found out from here. So this term will be coming over here. Okay. So heat transfer coefficient we can obtain in terms of phi only. Okay. If we proceed further to obtain the Nusselt number from this heat transfer coefficient, so then we can find out once again Nusselt number can be linked up with phi over here, because Nusselt number is nothing but h x bar by k. Okay, so h already we have found out, and x bar and k, if we link up with this one, cancellation of this x bar and x bar, root x bar and this x bar will be giving you root x bar at the denominator, and then we can find out that this term is u infinity x bar by nu. This will be giving you actually Rex. So root over of Rex by root 2 into phi 0. Anyhow, this Nusselt number is actually linked up with phi 0 once again. So we have found out if we can get this phi 0, okay, so all these wall temperature, heat transfer coefficient and Nusselt number can be calculated. By the way, to obtain this phi, what we need to do, we need to actually do the solution of this equation along with these boundary conditions. Okay, solution of this equation is actually coupled with your Blasius equation, F equation, which we have already showed in the previous lectures, which is nothing but f triple dash plus f double dash is equals to 0 along with the boundary conditions. Okay, so these equations are coupled equations and needs to be solved numerically taking iterative solver, and if you do that and find out what is the value of phi at wall, that means phi 0, then you can obtain this wall temperature, heat transfer coefficient and Nusselt number respectively. Okay. Little bit of side change from this Nusselt number and Rex can give you nu x Rex to the power minus half is actually a sole function of phi 0. Okay. Now here I will be introducing two different cases. One is for low Prandtl number limit, another one is for high Prandtl number limit. So if you do the solution, coupled solution for this phi equation and f equation for low Prandtl number limit, you will be finding out phi at wall and put in the equation of this Nusselt number. So then you will be finding out that this is actually the correlation what we get for low Prandtl number. Nusselt number Rex to the power minus half is equals to 0.886 Prandtl number to the power half. Okay, using your computational fluid dynamics knowledge, if you just do the analysis of these two coupled equations, phi equation and f equation, you can find out what is phi 0 for low Prandtl number limit, and this constant 8.886 will be coming from there. Okay. And similarly for the high Prandtl number tends to infinity, it will become 0.463 into Prandtl number to the power 1/3. Okay. Interestingly, you can see that Prandtl number to the power half for low Prandtl number and Prandtl number to the power 1/3 for high Prandtl number already we have shown in our constant temperature cases. So similar dependence also we are finding out over here. Only the values are changing over here from your constant temperature cases, only because the phi value we need to obtain from iterative solvers. Okay, so this part I am not going, but ultimately I am showing you that these are the equations we can obtain for the Nusselt number derivations for two different limits. Okay. Next, let us see that whenever we are having viscous dissipation, then how this equation is going to change. Okay, if you remember till now we have eliminated the viscous dissipation by considering very low Eckert number cases. Here this is very high Eckert number case. Let's say we are having viscous dissipation which cannot be neglected. So this term will be remaining over there. Okay, in the previous lecture I have showed you that phi star can be written as this one. Okay, so 2 del u del x whole square plus 2 del v del y whole square plus re to the power half del u del y plus re to the power minus half del v del x whole square. Okay. So here we have taken the transformation of small y to capital Y in this fashion. Y is equals to small y into r e to the power half, and transformation of small v to capital V we have taken in this fashion. Capital V is equals to small v into r e to the power half. Okay. So here if we try to find out that which term is dominating, once again just like the previous one, you will be finding out that this term is dominating, because x is very high, L is very high compared to your deltas. Okay, v and y, these are of same order, and here also v is very small compared to x. Okay, so all these terms will be actually not dominating with respect to this one. Okay, and if you take this r e to the power half outside with whole square, this will become RE, and this RE and 1 by RE can be cancelled from the equation. So ultimately Eckart number into del U by del capital Y whole square becomes the dominant term. Okay, all other small terms can be clubbed in this plus small terms. Okay. Now if you plug in this one in the equation of your energy form in case of constant heat flux, so the equation you will be finding out is changing in this fashion. Theta double dash plus Prandtl number f theta dash is equals to minus 2 pr f double dash whole square. So this extra term will be coming due to your viscous dissipation term. Okay, and subsequently boundary conditions are like this. Theta dash 0 is 0 and theta infinity is actually 0. Remember over here theta dash is coming in case of constant wall temperature, there was theta. Okay, because theta dash we need to keep for constant heat flux case. Okay, so heat flux is constant. Okay. Let me summarize what we have learnt in this lecture. First we have seen what is the choice of our temperature scale for non-dimensionalization of temperature. So unlike the previous one where we have seen the constant wall temperature case, the scale was TW minus T infinity. Here we cannot take that one, so we have chosen a intelligent temperature scale like QWL by K, okay, where K is the thermal conductivity, QW is the constant wall heat flux. Okay, and using this temperature scale we have showed that forced convection over flat plate having constant heat flux can be reduced in this form in terms of phi. Okay, so phi double dashed plus Prandtl number of phi dashed minus of phi f dashed is equals to 0. Okay, we have also derived the corresponding boundary conditions. Rather I can say that this boundary condition has been simplified from this temperature scale non-dimensionalization. So at eta equals to 0, phi dashed is equals to minus 1, and at eta tends to infinity, phi tends to 0. So this is far upstream, far away from the plate value. Okay, so this becomes 0. Okay, we have also mentioned the Nusselt number correlations for low Prandtl number limit and high Prandtl number limits. Okay, so Prandtl number tends to 0. We have shown that Nusselt number into Rex to the power minus half is actually 0.886 Prandtl number to the power half, and for Prandtl number tends to infinity, we have shown Nusselt number into Reynolds number to the power minus half is equals to 0.463 into Prandtl number to the power 1/3. Okay. At the end, we have also shown that whenever we take the viscous dissipation into consideration in the energy equation over insulated plate. Okay. By the way, if you go back to the previous one, here I have not mentioned this is for the insulated plate. Okay, so earlier till now we have discussed for constant heat flux. Here this is for the insulated plate. So QW is actually equals to 0. So in that case you will be finding out this equation is coming in this form, which also we have summarized in the next slide. So theta double dash plus Prandtl number f theta dash is equals to minus 2 Prandtl number f double dash whole square. Okay, and the corresponding boundary conditions are theta dash 0 is actually 0 and theta infinity is tending towards 0. Okay. Let me also test your understanding at the end of this lecture. We are having 3 questions. Okay. In case of forced convection over flat plate having finite heat flux, choice of temperature scale has been made from. So choice of temperature scale is very important. So we are having 4 options. Difference between wall and free stream. Next one, heat flux and thermal conductivity. then free stream velocity, and then none of the above, we take some other temperature scaling. Okay, so obviously you have understood because this was the prime thing in your lecture. So correct answer is from QW and K. Okay, QWL by K we have taken. Okay, second question is Nusselt number for forced convection over flat plate with constant heat flux will depend on, so we are having four options: Reynolds number, Prandtl number, both Reynolds number and Prandtl number, and none of this. So remember, this is for the constant heat flux case over the flat plate. So obviously we know the correct one is, it will be depending on both Reynolds number as well as the Prandtl number. Okay. Last question, which statement is not correct in the context of this lecture? Okay, so here I have shown three equations over here. First one is phi double dash plus Prandtl number into f phi dash minus phi f dash is equals to 0. Second one is theta double dash plus 2 f double dash square Prandtl number plus Prandtl number f theta dash is equals to 0. Third one is Nusselt number into Reynolds number to the power minus half is equals to 0.463 Prandtl number to the power 1/3 for Prandtl number tends to infinity, and all are not correct. Okay, so obviously you can understand that all these equations are not correct. Okay, so all are not correct is the correct answer. Okay. So thank you. Please visit our next lecture, which is about natural convection from a uniform wall temperature plate. And please keep on posting your queries in our discussion forum. Thank you.